Very important theorem here, thanks to our good friend Cauchy, which is the following. So say you have a certain contour, which can have any shape, basically. So this is C, contour C. And then you have a function f of z, which is analytical everywhere inside the contour. So the derivative is well defined. Then Cauchy tells us that the contour integral over this particular contour of f of z dz just vanishes. So that's a crucial result that we will be using over and over again in the future. So what I suggest you do now here is pause the video and take the first step towards a proof of this thing, which is the following. So I suggest you start from this expression. You parameterize this as a function of t, as per the definition of complex contour integrals. And then you split up both f and z into its real and imaginary components. And then you rearrange terms a little bit so that you end up with a separate expression for the real parts of this equation and also a separate expression for the imaginary parts of this equation. So pause the video and do just that. Okay, so here's our definition again. So we have the contour integral of f of z dz over c. That's going to be parameterized as an integral over t, a parameter t running from a to b, where z then fundamentally depends on t, and then also dz as a function of t, we can write this as z prime t dt rather, not dz. Okay, so now let's just expand this a little bit into real and imaginary parts. So f consists of a real part u and an imaginary part v. So u will depend on z, obviously. So u will depend both on the real and the imaginary part of z. So u will be a function both of x and y. But more importantly, both x and y, they're also depending on t. So we integrate over t. So this is the real part of f. And then we can also write that jv depends through x and y on t. So v is a function of x of t and of y of t. So this is our first factor. Then for our second factor here, z prime of t, well, that we can just simply write as z being equal to x plus jy. We can write this as x prime of t, so the derivative of x with respect to t, plus j derivative of y with respect to t dt. So that's just the definition of parameterization to calculate this particular integral here, and then splitting this up into real and imaginary parts. It looks a bit unwieldy with all of these explicit dependencies on x and y and t, so let's lighten our notational load a little bit and let's get rid of all of the arguments and just say that here we write this as u plus jv. But remembering that both of these are functions of x and y, and then x and y are functions of t. And then for the right-hand side, for the second factor here, well, let's have a look. What we have here are terms like x prime t dt. X prime, remember, this is basically the derivative of dx dt with respect to t dt. So we can write this in a bit more compact form as simply dx. So if we do that, we can write here dx plus j dy. So it's the same thing, but in a much more compact form, but it's very important to remember that what we're integrating over here is not fundamentally the x and dy, but this is fundamentally an integral over dt. This is just a notational shorthand to make our life a little bit easier so that it's much more straightforward to expand this here and then come up with an expression for the real and the imaginary parts of the results. So for the real part, that's going to be an integral from a to b of u dx minus v dy. Okay, so that's the real part. And then the imaginary part of the end result is an integral from a to b of v dx minus u dy, plus u dy rather. Okay, so here we explicitly have the real part of the result and the imaginary part of the result. And again, remember, it's not that dx and dy, they're independent, so we're not integrating over an independent dx and dy, but fundamentally we're integrating over dt again. So this is just a real valued integral over dt. Good. If you look at this, this looks a lot like what you know from your kindergarten vector analysis calculus, namely as line integrals of vector fields. So not scalar fields like we used in the definition of our line integral of complex functions, but this time of vector fields. Just a quick recap of that particular situation. So if you have a certain curve C, and if you have a vector field A of R, so a vector field is an object which takes in a certain position and spits out another vector, so vector in, vector out. Not vector in, scalar out, like in the previous videos. So if you have this vector and you take the scalar product with the elementary displacement dr, then this particular case was defined again by parameterization as an integral from a to b over our parameter t. Just as you would expect, it's defined as a of r of t. And then this second thing becomes r prime of t dt. So this is the definition of a line integral of a vector field. And actually, you can also write this using the same type of shorthand, basically, as an integral of ax dx plus ay dy plus az dz. So that's the same thing which you either get from expanding this in components or by using the same argument as we did here, writing this here as dx, dy, or dz respectively. But again, remember, this is an integral over t fundamentally. So if you compare what we have here, that looks very suspiciously to like what we have up here. Why am I saying this? I'm saying this because this will be useful later on. So first of all, it gives us a different way of interpreting the results of a complex integral, namely as a result where both the real part and the imaginary part can be written as regular integrals of vector fields, real valued vector fields. But more importantly, the reason why I bring this up is because we will need it in order to be able to apply the Cauchy-Riemann conditions. Because remember, we might have lost track of what we really want to do. We want to calculate this particular integral in case the Cauchy-Riemann conditions hold, and then show that the result of this integral is 0. We're going to do that by proving that both the real part and the imaginary part are 0. But in order to be able to apply Cauchy-Riemann, we need stuff like partial derivatives. And at this point in time, there's no partial derivative of u and v and psi. So that's a problem. Luckily, we can rectify our problem by making use of another good mathematician friend called Stokes. Stokes basically told us that if you have integrals like this here, so if you have an integral of a dr over a certain curve, closed contour, that you can also write this as a surface integral over the inside of our contour. Not of the function a, but of the curl of a. And then ds is a vector perpendicular to our surface. So if you have here a contour C, and we have an internal region S, a surface, and then ds is just perpendicular to that surface. So this looks like it could be handy because this will bring us all the partial derivatives here. So what I suggest you do now is pause the video and simply rephrase this equation of Stokes for the case of a two-dimensional situation. So what we're dealing with, so without a z component. So pause the video and simplify Stokes to the two-dimensional case. So in the two-dimensional case, there's no AZ. So AZ is basically equal to 0. And then for the left-hand side, we can write this, if we expand this, as AX dx plus AY dy. So that's very simple, the left-hand side. For the right-hand side, we have this, this expression over here. But remember, in the 2D case, S is entirely contained in the xy plane. So if we're perpendicular to that, this means that this vector ds is in essence along the z direction. So if we take the dot product here, this means that we're only interested in the z component of the curl of our A here. So if we calculate that, we have the determinant I, j, k, and then the partial derivatives dx, dy, there's no dz. And then we have ax, ay, and again, no z component. So for the whole z component of the curl, we just get rid of this line and this column, and then we take this little sub-determinant here. So we get the derivative of ay with respect to x, derivative of ay with respect to x, minus the derivative of ax with respect to y, integrating over dx and dy, of course. Right? So this is Stokes reduced to the two-dimensional case. Now let's see how we can use this. So if we go back to, for example, this expression over here, let's now apply Stokes and the Cauchy-Riemann conditions to this expression to show that the end result is 0. So that's a nice thing you can try for yourself. Pause the video to do so. So what we're looking at is this integral here, u dx minus v dy. So let's copy that again. So we have the integral of u dx minus v dy. And this is of the form that we have here, ax dx plus ay dy. Simple identification tells us that ax is u and ay is minus v. So if we just write down Stokes telling us that's dAy dx minus dAx dy, okay, dx dy. This becomes the integral, so ay is minus v, so we have minus dv dx and then minus du dy dx dy. And thanks to Cauchy-Riemann, this thing vanishes because this is exactly one of the Cauchy-Riemann conditions. Okay, that's half of the work done. We know that the real part is 0. So pause the video and do something very similar to show that the imaginary part is 0 as well. Very similar here for the imaginary part. The integral is, if we scroll back, so what do we have here? We have, where do we have it? We have this particular integral, so v dx plus u dy. So now we have the integral of v dx plus u dy. So trivially, ax is v and ay is u. So this now becomes the surface integral of the partial derivative of u with respect to x minus partial derivative of v with respect to y dx dy. And again, this is another one of the Cauchy-Riemann conditions that tells us that this thing vanishes as well. So now we've finally shown that the whole contour integral of f of z dz is equal to 0 if f of z is a holomorphic function.